Hello everyone, welcome back to our channel. So today we are going to see about the holders inequality. In order to cover the syllabus for the internals, and here right now saying only about the holders inequality and its purpose and its proof for other inequalities also. So that in the internals they might mostly ask the statements and the proofs. So if I get some more time, then I will post the videos of applications and limitations also. Just in order to focus on our internals, I'm just taking this part as important and posting it to you. Now let us learn what is holders inequality. It provides an upper bound for the integral of the product of two exponents or random variables given their individual integral properties. So first let us learn what is integral. When there exists an integrable function, which is nothing but when the expectation of a random variable is finite, which is nothing but expectation of x should be less than infinity, then only the integrable function exists, right? Which is expectation of x is nothing but integral x into f of x dx, right? If this integral is finite, then only the integrable function will exist. And we have, it provides an upper bound for the integral of the product of two exponents or random variables. Let us take random variables, which is nothing but x and y. And here it is saying the integral of product of two exponents or random variables. So, which is nothing but expectation of xy as we are solving the inequality theorem, which is less than or equals to, given their individual integral properties, which is nothing but expectation of x into expectation of y. This is the individual integral properties. And now here we are considering the two exponents. So the exponents may be, which can be considered as moments, the 1 by pth moment or 1 by qth moment. So I can write it as the random variable, this random variable expectation of x to the pth moment, which is 1 by p. Therefore expectation of x into p whole to the power of 1 by p and expectation of y to the power of q whole to the power of 1 by q. I can write it as 1 by q. These type of upper bounds are provided by the holders inequality. Now let us see what is its purpose and what is the interrelationship between the other inequalities. Let me remove all this. Now if you not have watched the previous videos, I request you to watch them. The purpose is, it is applied in probability theory to bound movements and expectations of random variables. ఇక్కడ మనం probability థియరీలో ఈ holders inequality అనేది దేనికి యూస్ చేస్తాం? In order to find out the moments, which is nothing but the mean, the first central moment, mu, we can call it as, and variance, which is nothing but the sigma square, and the third central moment, which is mu3, and fourth central moment, which is mu4. In order to know this bounds in probability theory, we use the holders inequality. And the next one is establishing inequalities. It is nothing but ఈ holders inequality ని యూజ్ చేసి మనం ఇంకా వేరే inequalities ని కూడా ప్రూవ్ చేయొచ్చు. So the holders మినికౌస్కి ఇన్ఈక్వాలిటీ ప్రూవ్ చేయాలంటే కంపల్సరీ మనం దాంట్లో హోల్డర్స్ ఇన్ఈక్వాలిటీ లేని మనం మినికౌస్కి ఇన్ఈక్వాలిటీ అనేది ప్రూవ్ చేయలేం. కంపల్సరీ ఇన్ ది ప్రూఫ్ you need to use the holders inequality. So please be careful while learning the proof of this inequality. And we also have the Cauchy-Schwarz inequality, right? Do you remember it? And this holders inequality is a special case of Cauchy-Schwarz inequality which can be used in quantums, quantum mechanics, and linear algebra, LA, and also statistics. And now let us know what is the interrelationship between the holders inequality and other inequalities. The one that we learnt is the holders inequality is a special case of Cauchy-Schwarz inequality, and holders inequality is used to prove the Minikowsky inequality. Now let us learn what is the interrelationship between the Chebycheffs inequality and the holders inequality. In the Chebycheffs inequality, we use mean and variance, right? By using these both components only, we will find out the upper bound, which is nothing but the Chebycheffs inequality is limited to two exponents. These two exponents only, the first two exponents. But in the holders inequality, it will take any two components, any two pair of components, any two pair of components or exponents we can call it as, which is nothing but 1 by p is one exponent and 1 by q is another exponent. So by using the rth exponent, we can find out the upper bound. This is the difference between the Chebycheffs inequality and the holders inequality and their interrelationship. And now let us see the statement and proof of this inequality.
State and prove holders inequality. Using this inequality only, we are going to prove the other inequalities. So please be careful while state and proving this inequality and don't skip the video. The statement is, let p comma q be any two real positive integers. Two real positive integers. In the internals also, they might be asked you the statement like in the holders inequality, what is p comma q, whether they are positive integers, real positive integers, or negative integers, or none of the above, in this way. So you need to be very careful while learning the statements and proofs. Real positive integers and 1 by p plus 1 by q is equals to 1, and this p comma q always lies between 1 and infinity. Therefore 1 less than p comma q less than infinity. Then if you consider the two random variables x and y, their expectations are finite, which is expectation of mod xy comma expectation of mod x comma whole to the power of p and expectation of mod y whole to the power of q is less than infinity. So we need to prove expectation of mod xy is less than or equals to expectation of mod x p whole to the power of 1 by p into expectation of mod y to the power of q whole to the power of 1 by q. So now, in order to prove this inequality, I am using the Young's inequality. So the Young's inequality is a to the power of p by p plus b to the power of q by q is greater than or equals to ab. This is the Young's inequality. Okay. Now consider the A has mod x divided by expectation of mod x to the power of p whole to the power of 1 by p, and b value has mod y by expectation of mod y whole to the power of q into whole to the power of 1 by q. Consider A and B value as this one. Now substitute these values in the above Young's inequality. So you get mod x by expectation of mod x to the power of p whole to the power of 1 by p divided by, we have divided by p plus mod y by expectation of mod y whole to the power of expectation of mod y to the power of q whole to the power of 1 by q divided by q greater than or equals to mod x divided by expectation of mod x to the power of p whole to the power of 1 by p into mod y by expectation of mod y to the power of q whole to the power of 1 by q. So now we have a to the power of p and b to the power of q. So this whole will get p and this whole will get q. Now mod x to the power of p. Here for this whole expectation we have 1 by p. If you multiply this p by p, then the p and the numerator p and the denominator p will be cancelled. So you get only mod x to the power of p by expectation of mod x to the power of p. And for mod x to the power of p by expectation of mod x to the power of p. Okay, and this p I can write it as 1 by p, right, which is nothing but a by b by c by d is equals to a by b into d by c. Here the, if you consider, for suppose a is mod x and b is expectation of mod x to the power of p, then c is this one and d is 1. Then a by b is this one. Then d by c. D is 1, therefore 1 by p. And plus mod y to the power of q divided by, here also the whole, for this whole you have to the power of 1 by q. So if you multiply this q divided by q, which is equals to, we can cancel numerator q and denominator q, therefore you get power 1. So you have expectation of mod y to the power of q, and I can write this denominator q as 1 by q, 1 by greater than or equals to mod xy divided by expectation of mod x to the power of p whole to the power of 1 by p into expectation of mod y to the power of q whole to the power of 1 by q. Now apply the expectation on both sides. Then you get expectation of mod x whole to the power of p by expectation of mod x to the power of p into 1 by p. Already here you have expectation, so you no need to apply once again. Here the expectation is not there, so you will apply the expectation here. Okay, plus already you have expectation here, so I'm applying expectation of mod y to the power of q by expectation of mod y to the power of q into 1 by q greater than or equals to expectation of mod xy divided by expectation of mod x to the power of p whole to the power of 1 by p and expectation of mod y to the power of q whole to the power of 1 by q. Then easily you can cancel this one, then you get 1 by p plus 1 by q. We know that 1 by p plus 1 by q is equals to 1 from the statement. Therefore, from the statement we have 1 by p plus 1 by q is equals to 1. So I can write here the 1 by p plus 1 by q is 1 less greater than or equals to expectation of mod xy divided by expectation of mod x to the power of p all to the power of 1 by p into expectation of mod y to the power of q all to the power of 1 by q. So if I send this term to this side, then it will become expectation of mod x to the power of p all to the power of 1 by p into expectation of mod y to the power of q all to the power of 1 by q is greater than or equals to expectation of mod xy, which is nothing but expectation of mod xy is less than or equals to expectation of mod x to the power of p whole to the power of 1 by p into expectation of mod y to the power of q is whole to the power of 1 by q. This is what we need to prove from the statement. So we can write hence proved.